Good morning students. Now we are going to study about radial wave function, that is denoted as psi, or it also called some inside textbook R. You can write any one. Okay. Radial probability function. First we are going to discuss the radial wave function, and then we are going to start a radial probability function. Before going to radial wave function, the psi is wave amplitude. Psi is wave amplitude or wave function. Psi or R. Already I told you that. Okay, if psi square or R square is probability density. Okay, this is nothing but I am telling only the terms. Now we are going to definition. When psi is taken as function of R, distance of the electrons from the nucleus. You see, if you talk while I am writing this diagram, this is the radius, this is ER, means you see this is radius. For example, this you take a nucleus only, this is R, this is electrons. The distance between the electron and nucleus is R. Its function means R, small r function is nothing but psi. When psi is taken as a function of R, distance of the electron from nucleus is called radial dependence or radial wave functions. Okay, this is nothing but what we defined. Now we are going to write this graph, means boundary, means you can tell that graphical or plot between the psi and R. This is for 1s orbital. If you take 1s orbital, the principal quantum number is 1, correct? No, the principal quantum number is 1. Therefore, what is a azimuthal quantum number? Azimuthal quantum number formula, you know, L is equals to n minus 1, correct? No, n minus 1. If you make it, you will get L is equals to 0. Then azimuthal is 0. Then you see the plot when function of a radius increases, quite commonly the radius is increasing, that time the function will be decreases in 1s orbital. Very very important for comparative this graph. And now we are going to second 2s orbital. If you take 2s, principal quantum number is 2, correct? No, then azimuthal is 1, but it starts from 0, correct? No, 0 1. You see what happens is, starting from the origin, it goes on decreases with the radius increases. Suddenly it moves to positive to negative. See, positive to negative, it touches the 0 point. Okay, means the graph going towards 0, then this point is nothing but node. I will next I will explain the definition of node. Okay, again it increases the node. Did you understanding here? Again it increases the node. If radius increases in 2s orbital, the wave function goes on decreases and suddenly it will be increases. It moves from positive to negative in 2s orbital. You want to remember this point. Okay, next we are going to talk about 2p orbital. 2p orbital, you see this here what we happen, same the plotting the psi in y-axis, in x-axis or radius of the atom. You see here what happens, it goes on increases. When radius increases, the function of the radius also will be increases. So on certain time it starts to decreases. This maximum point, increasing point is nothing but if you take it is CR, critical radius. We will talk this critical radius. This point can find the maximum number of electrons. This point means critical radius can find the maximum number of electrons. Okay, this is nothing but a radial wave function. Next we are going to talk about node, because I already told what is node, correct? No, You see, if you go to talk a node, you see, a wave function node occurs at a point means it occurs at a point where the wave function is a zero. Wave function is a zero and changes the sign. No, yeah, because it's positive, it will be negative. If you plot a graph, positive, negative, correct? No, it from passing from like this. For that we are telling it changes the sign. The electrons has zero probability of beginning located at the node. Beginning, this is the beginning. Again here beginning, correct? No, it starts here. First here beginning, here it comes and it starts again. It's beginning here onwards. Okay, this is nothing but node. A formula for node for ns orbital. Ns is equals to n minus 1. For s orbital, if we talk similarly p orbital n minus 2, d orbital n minus 3, f orbital n minus 4. For example, you take 1s is equals to n is nothing but 1. No, 1 minus 1 is equals to 0. It is a 0 node in 1s orbital. If you take 2s orbital, 2 minus 1, it is 1. You see, the s orbital, first starting the s orbital, if we take any orbital, if you take s, p, d, f, it starts 0 only. For example, in 1s it becomes 0, for 2s it becomes 1, correct? No, yeah, p. Now similarly, if you take a p, 2p is equals to 2 minus 2 is 0. You see what I told, 0. Similarly, d and f, it starts from 0 only. Nodes will start from 0 only for particular orbitals. Okay, for next we are going to talk about radial probability density. Radial probability density. You see, what is radial probability density is nothing but radial probability density is denoted as psi square or r square. Psi is nothing but radial wave function. No, it's square. The square of the radial wave function is known as a radial probability density. The square of the radial wave function is known as a radial probability density. Okay, it gives the probable density of the finding the electrons. It gives by plotting the means it gives the to find the probable density means we know that density is nothing but mass by volume, means electrons mass and volume we can find in probably finding the electrons. Okay, at particular point means which point, for example the radius, if you take the position in the, it is the position of the electrons. When come to Heisenberg, it told that we cannot find the position and momentum, correct? No, here we are telling the radial probability we can find the position. Okay, position. We are understanding the particular point along the radius line also we can find the electron at particular point along the radius line. Okay, plotting, similarly what we plot in radial wave function, similarly what no changes occurs in 1s orbital. I am not telling that a node because I already explained that. I am not explaining what is principal and azimuthal, because you can write this 1s means n is equals to 1, l is equals to 0, correct? No, for you see now we are plotting from psi square by r. Okay, plotting. Okay, it gives the nearest nucleus. This plot gives the nearest nucleus. Okay, the changes occur in 2s orbitals. You see 2s orbitals in the radial wave functions. What happens? It goes from positive to negative, but here not going to it's not changing the sign. You are understanding here? It moving towards the node. It goes to 0 and it does not goes to the negative. It starts here only. This is node only. Okay, this is 2s orbital plot. And I don't want to explain the principal and azimuthal. You know that already. Similarly, when the radius increases, the radial probability function of radial probability density will move along the radius. According to graph, you see, according to graph, 1s and 2s are the maximum density. You see, 1s and 2s having a maximum density at nucleus. When come to 2p, you see 2p is it moving almost zero electron density at nucleus. You see its maximum density, where 1s and 2s is maximum density. When come to 2p, it having electron density is 0 at nucleus. All the orbitals other than S, the electron density is 0 at nucleus. We can take 2p or 3p or 4d or 3d, okay, and 4p. You see p and d and f orbitals. If you take it all, electron density is 0. Okay. Next we are going to talk about radial probability. Radial probability function. You see, radial probability function is nothing but, you see, first we talk on that radial wave function. While radial wave function square, it makes the radial probability, while it differentiate, means radial probable function is also called as RDF. RDF, okay. You see, what is this RDF? If you take a orbital, this is a nucleus, correct now? I am taking the orbital. This is nothing but dv r. Okay, r they can also differentiate because the number of electrons will be there. The total probability of finding the electron, in small region like S, okay, small region is to determine the volume of the region. Already the previous I told in radial probability, mass and volume. Here they determine the volume of the region. You see, volume of the region, it is a dV. Volume of the region. For that only I call that dV. How much volume is occurring from nucleus to electron. Okay, do you understand this? The radial probability function will determine the volume of the region in small regions. Okay, to determine the volume of the region at small regions. Okay, the product of the probability electron density is corresponds to volume, means product of the probable electron density and corresponding volume of the space, means how much space is occurring in between. Okay, the volume is RDF. You see, volume of the sphere is 4 by 3 pi r cube. Volume of the sphere is 4 by 3 pi r cube. If you take r and you see, dV is nothing but means volume of the sphere, volume of the orbitals, 4 pi r square by dr. 4 pi r square by dr. If probability is equals to psi square into dV. If you substitute the 4 pi r square dr, we will get 4 pi psi square into 4 pi r square dr. If you multiply both 4 pi r square dr psi square. This is the formula to find the radial probability function. Okay, you see, next we are going to write the graphs of the radial probability function, that is dV by r. Our dV we know that 4 pi r square dr. We can write any one. Okay, if you take any one, it will you see, for 1s orbital it is the maximum probability to find the electrons. Maximum probability of finding the electrons. It's I already told that CR, critical, means maximum finding this point. No, this point is 529 picometers. 529 picometers for 1s orbitals. Okay, similarly if you talk for 2s, this is dV in y-axis, r is x-axis. If you take it, start from origin and it having a node. You see, this is a node, what we telling, but this is not a node, this is the origin, this is a node. Okay, node, and again it moves in the same sign with increasing. Okay, it's 2s orbital is 270 picometers. When come to talk about 2p orbitals, when psi square, dV or 4 pi r square by dr in the x-axis r square, it goes on. If the radius increases, the volume also increases, suddenly it will decreases. It's the maximum point to find the electrons density is 290 picometers. Next we are going to talk about shapes of the atomic orbital or boundary surface diagram. Okay. You see, in 1s orbital, we taken this atom, we are passing x, y, z axis. 2s orbital, okay, we are passing same. You see, the increases the radius, correct? No, in 1s orbital, okay, and 2s orbital, we are taking only s. You see, in s orbital, what happening? I am writing same this the diagram in already. See, in 1s orbital we taken x, y, z axis, correct? No, similarly in 2s also. You see, a node is occurring. Node is occurring in 2s orbital. This is the node. Okay. You see, in s orbital we talk the subshells. Subshells. When what happens in s, L is equals to 0 quite commonly, and ml is equals to mathematical quantum number is equals to 0, then it is a spherical shape. It has a spherical shape. We have the formula to find node, that is ns is equals to n minus 1. 1 minus 1 is equals to 0. ns will start from node is 0. The uniform electron density along the 3 axes. You see, uniformly electron density will be occurring, okay, in 3 axes, that is x, y, z axis. If you see the radius, the 4s orbital is greater than 3s orbital, 3s orbital is greater than 2s orbital, 2s orbital is greater than 1s orbital. You see, in 1s orbital higher energy is there. When come to 4s, lower energy. Why it is 4s low energy? Because the radius is more. Radius is more, for that it having a low energy. Okay, next we are going to talk about p orbitals. You see, while coming to p orbital is a p subshells quite commonly. Now we are going to talk about the p orbitals. P orbitals having the p subshells quite commonly. You see, the p subshells, we know that already the L is equals to 0, 1, 2, 3. If L is equals to 0, it is s orbital. If L is equals to 1, it is p orbital. 2 is equals to d orbital. L is equals to 3, it is p f orbitals. Okay, f orbitals. If you talk a subshells, ml is equals to L plus 1. For p orbitals, L is equals to, quite commonly, p is nothing but 1, correct? No, 1. 2 into 1 plus 1 is equals to 3. If we got a 3 means, first we want to start from 0, because, correct? No, the magnetical momentum starts from 0 and minus plus. Okay, do you understand this? We got a 3. 3 possible orientations are occurring. You see, in p orbital, that orientationally occurring. You see, the orientationally occurring. This is a px, because it, the dumbbell shapes are passing in, it is a dumbbell shape, it is passing in x-axis. It is passing in y-axis, that is for py. If it passing in z-axis, it is pz. Okay, pz orbitals. Do you understand here? It is a dumbbell shape. It has a dumbbell shape. Okay. When if you fill the electrons, the px having the plus 1, we got that plus 0 minus 1. No. If you passing means if you pass the filling the 3 px, py, pz. Okay, if you passing px is equals to px is equals to what? It is plus 1. Py it is 0. It is pz is minus 1. Plus 1, 0, minus 1. Okay, do you understand this? Okay, next we are going to talk about d orbitals. The d orbitals, you see, while talking about d orbitals having a d subshells. Correct now? The d orbital having d subshells. You see, the d subshells, what is the n is equals to 3. N is equals to 3, L is equals to 2, because already I told that L is equals to 2 means it is d orbital. In p orbital, while explaining the p orbitals, then while if you calculate ml is equals to, ml formula we know that ml is equals to 2l plus 1. 2l is nothing but 2 into 2 plus 1 is nothing but 5. 0, 1, 2, 3, 4, 5. Correct now? Or 1, 2, 3, 4, 5. You got 5. You see this, we getting a 5. And the 5 different orbital, 5 orientation. 5 different orbitals with the 5 orientations. That is dxy, dyz, dzx, dx square minus y square, dz square. It is a shape, that is cover leaf shape and donut shape. You see, donut shape is occurring here. While you see, this is dxy. Why you call it dxy? You see, in the x-axis the both the lines are passing, correct? No, you see in the x-axis both the leaves shape like donut shapes will be occurring. Okay, that is called dxy. Similarly, welcome to dyz. You see dyz is also same, dzx, dx square minus y square, dz square. Dz square we got that very uniquely, that is doubly. Okay, it's complete the radius of the wave functions and radial probability function, radial and shapes of the orbitals. Okay.